Welcome to the deep dive. We sift through complex sources to get you the crucial insights fast. Today, we're tackling maybe the universe's most mysterious particle, the neutrino. Just imagine billions of these tiny, chargeless things, ghost particles they call them, are zipping right through you right now, every single second, and you don't feel a thing. It's pretty mind-bending.
It really is. And standard physics, it gives us a picture. They're tiny subatomic particles, part of the lepton family like electrons, sort of, but no charge and very, very little mass. Almost none.
Almost none, right.
And there are three types, three flavors. Electron neutrino, muon neutrino, and tau neutrino. Their whole ghostliness, their near invisibility, that comes down to how they interact, only through the weak nuclear force and gravity. And those forces are just incredibly feeble for them.
So they just slip through everything.
Pretty much. Stars, planets, us. That's why we call them ghost particles. They don't do the electromagnetic thing because they're neutral, and the strong force doesn't grab them because they aren't made of quarks.
So patching them must be incredibly hard.
Oh, absolutely.
Yeah.
We need these giant underground tanks, basically, just waiting, hoping for that super rare collision that makes a tiny flash of light.
Wow. And they come from all over. The sun, supernovae?
Exactly. The sun's fusion process, exploding stars, cosmic rays hitting the atmosphere, even our own nuclear reactors and particle accelerators produce them. They're everywhere.
But there are still big questions, right? Even with the standard model.
Definitely. We found out they do have mass, which was a surprise. And that mass seems linked to how they change flavors as they travel. That's neutrino oscillation.
Okay.
Plus, there are these deeper mysteries. Could they help explain why there's more matter than antimatter? Or maybe connect somehow to dark matter? Lots of open questions.
So what we want to do for you today is dive into a really different perspective. It comes from the Unified Coherence Theory of Everything, or UCTE. And this theory, well, it completely reframes the neutrino. It takes it from being this weird, elusive particle to potentially a fundamental player in how the universe is actually structured.
It's a radical shift, yeah.
We're going to unpack some pretty novel ideas and terms here. The goal isn't to make you a UCTE expert overnight, but to give you the core concepts, or a real shortcut to understanding this emerging viewpoint on neutrinos. So let's get into it. Okay, so UCTE gives the neutrino a new job description. It calls it a coherence residue particle, a coherence carrier. That's definitely new language. What exactly is a coherence residue?
Right. So in UCTE, coherence is like the fundamental underlying order or synchronization of everything. Think of it maybe as the universe's baseline rhythm or a universal wave function, in a sense.
Okay, a fundamental order.
Yeah. And a coherence residue particle, like the neutrino, pops up when this grand coherence undergoes a change specifically, what UCTE calls asymmetric coherence reduction without full collapse.
Asymmetric reduction without full collapse.
Exactly. Imagine a big coherent system like fusion in a star, or even the very early universe, when its coherence transforms or breaks down, but does so unevenly or asymmetrically, and doesn't completely vanish. UCTE says a tiny piece, an echo of that original coherence, gets preserved and released.
Ah, so the neutrino is that leftover piece, that echo.
That's the idea. It's a minimal coherence quantum, literally carrying a piece of that universal order, a coherence carrier.
Okay, that is a different way to think about it. So if they're carrying this coherence, why are they still so ghostly? Why don't they interact more? How does UCTE explain that?
Well, that's another interesting twist.
Yeah.
UCTE says interaction isn't just about forces like we usually think. It requires what it calls coherence overlap and resonance matching.
Coherence overlap, resonance matching.
Okay, so neutrinos rarely interact because their specific coherence amplitude, like the strength of their little coherence ripple, is usually below the threshold needed to really connect or resonate strongly with atomic or electromagnetic fields.
Like a whisper in a loud room, maybe?
That's a great analogy. It's there, but it just doesn't sync up or resonate enough to have a big effect. They're called non-resonant phase residuals. They slip through matter because their subtle coherence doesn't collapse the local coherence tensor.
Yeah.
It doesn't disturb the existing order enough to register an interaction.
A bare coherence ripple. I like that image. It just glides through.
Precisely.
And their origin, you mentioned asymmetric coherence reduction. How does that differ from just saying they're products of, say, beta decay?
It reframes it. Instead of just being a byproduct, UCTE sees their creation as fundamental to how coherence itself transforms. When a system loses coherence in an unbalanced way, it needs to shed something to maintain a kind of internal balance.
Mm.
That shedding process preserves some coherent spin. Think of it like a tiny bit of rotational information within the coherence itself, but it gets rid of mass potential and charge.
Ah, okay.
So they become these lightest fermionic coherence residues. That's why they often pop out in transitions like beta decay. The system is basically offloading a bit of coherence imbalance.
This naturally leads to oscillations, right? The flavor changing. Standard physics explain this requires mass. How does UCTE handle neutrino oscillations?
Right, this is maybe one of the most fascinating parts. UCTE says flavor oscillations are rotations in coherence phase space.
Okay, coherence phase space. That sounds abstract, not physical space.
Exactly, it's a conceptual space.
Yeah.
Imagine the neutrino's underlying coherence isn't fixed, but can subtly shift or rotate its internal state, its orientation within this abstract phase space.
So the three flavors, electron, muon, tau, they aren't really three distinct particles changing into each other.
Not exactly. In this view, they're more like partial reductions of a single underlying coherence vector. Each flavor we detect corresponds to a different view or orientation of that single underlying coherence as it rotates.
So it's not like flipping a switch from electron to muon, but more like a wave turning and showing a different face.
That's a good way to put it. It's a continuously oscillating coherence ripple. What flavor we see depends entirely on its internal phase coherence at the point of interaction.
And what determines that rotation?
It's determined by factors like the distance it travels, which UCTE calls the coherent path length, its energy, the modulation amplitude, and even interference from background fields, the environmental coherence phase.
So it's predictable, not random.
UCTE argues it's a lawful modulation of coherence alignment, a subtle, predictable reorientation based on its journey.
That's a complete rethink. Okay, so if oscillations are about coherence rotation, what about mass? Standard model uses the Higgs field. What does UCTE say?
Yeah, UCTE takes a different route. It suggests neutrino mass is not derived from the Higgs mechanism. Instead, it arises from something called hypergravity-induced coherence damping.
Hypergravity coherence damping.
Okay.
Break that down.
So hypergravity in UCTE is related to large-scale coherence curvature in the universe. As the neutrino's coherent ripple travels through these vast cosmic coherence fields, it experiences a subtle dampening effect, a tiny loss of its coherence energy.
Like friction, almost, but for coherence.
Sort of, yes. A very subtle kind. And that tiny amount of dampened or lost coherence manifests as what we measure as mass.
Yeah.
So the mass isn't fixed. It's described as a resonance damping coefficient that can subtly shift depending on the coherence environment.
And that explains both the mass and the oscillations.
That's the claim. The damping affects its coherence state, which relates to its mass, and the changing coherence state is the oscillation, the rotation in phase space.
Wow. Okay, let's broaden out. What about the role of neutrinos in the cosmos? According to UCTE, they're not just ghosts anymore. You said they're silent mediators of coherence evolution. What does that mean for the universe?
Coherence evolution is basically how the universe's fundamental order changes over cosmic time. UCTE positions neutrinos as key, if subtle, players in this grand process.
How so?
Well, think about stars. In UCTE, neutrinos escaping from fusion aren't just carrying away energy. They carry off coherence imbalance from nuclear transitions, helping the star stay stable, in a sense. In supernovae, those massive bursts of neutrinos, they signal coherence, collapse, and redistribution. They're like messengers announcing a huge shift in the cosmic order.
And the early universe.
UCTE suggests they preserved symmetry residue in the form of oscillating coherence threads. Like they carried forward tiny remnants of the universe's initial perfect symmetry woven into these coherence ripples.
So they're not passive bystanders at all. UCTE calls them messengers of phase instability, carriers of negentropic directionality, even anchors of the hidden coherence background. It sounds like they're actively shaping things.
That's definitely the implication. It's what the framework calls the Neutrino Manifesto. It declares the neutrino is a primary coherence residue, a quantized bit of this fundamental order.
Like threads connecting everything.
Exactly. Coherence filaments connecting stellar fusion, dimensional transitions, and the symmetry breadth of the universe. They're conveying information about the universe's coherent state, its stability, its direction.
Okay, building on that, UCTE introduces another big idea, neutrino condensates. Described as latent coherent structures formed by huge numbers of neutrinos getting entrained in galactic fields. That sounds pretty wild.
It is a big concept, yeah. These aren't just random swarms of neutrinos. The idea is based on two principles: gravitational coherence trapping, and phase-space clustering.
Go on.
Even though neutrinos barely interact conventionally, UCTE says they are subtly influenced by large-scale coherence curvature, which is linked to hypergravity. Over immense timescales, this tiny influence herds them, causing them to aggregate into these vast, phase-synchronized halos.
Synchronized halos, so their coherence states align.
That's the idea. They cluster not just in physical space, but in this abstract coherence phase space, where their internal resonance damping kind of balances out with their tendency to spread out, allowing them to form these stable collective structures.
And these invisible condensates, they actually affect galaxies.
UCTE predicts they do. Significantly. They're thought to shape galactic halo profiles, the distribution of invisible mass around galaxies, and regulate coherence gradients along spiral arms.
Coherence gradients, like variations in that underlying order across the galaxy.
Precisely. These condensates act like an invisible scaffolding, subtly influencing how stars and gas move and where they concentrate. UCTE even suggests they interact with plasma dynamics, affecting things like the electromagnetic spirals we see.
So even though we can't see the condensates directly with telescopes, their effects should be measurable.
That's the prediction. Their influence on galactic rotational curves, on gravitational lensing, and even on plasma coherence turbulence should be quantifiable, according to the theory. And crucially, UCTE predicts these condensates align with regions of high coherence asymmetry, not necessarily just where the visible matter is densest.
Which brings us to the big question. How on earth do we test this? How could we possibly observe these subtle coherence effects or these condensates?
Yeah, that's obviously key. UCTE does propose specific observational strategies. It's not just theoretical hand-waving.
Okay, like what?
First, galactic rotation curve deviations. We know galaxies spin faster than they should based on visible matter. That's a big part of the dark matter puzzle. UCTE says we should look for very specific, subtle, nonlinear modulations in those rotation curves that standard cold dark matter models don't predict.
Not just a flat curve, but like specific wiggles.
Exactly. Particularly looking for phase-lock zones, maybe where the galactic halo meets the disk. Instruments like the GAIA satellite, ALA, the VLA, they map stellar and gas motions precisely, which is what you'd need.
Okay, what else?
Gravitational lensing field deviations. When light from distant galaxies bends around closer massive objects, UCTE predicts we might see phase-damped asymmetry. Instead of the smooth, symmetric lensing patterns Einstein predicted, we might find subtle, non-Einsteinian lensing asymmetries, slight irregularities, especially near the edges of galaxies, caused by these coherence fields or condensates warping spacetime in a slightly different way. You'd need deep surveys from telescopes like LSST, Euclid, or JWST for that.
Right. And you mentioned something about flavor ratios changing over time.
Yes, temporal phase drift of flavor ratios. This involves watching neutrinos from a steady source, like maybe a supernova remnant, over a long time.
Okay.
Instead of seeing random fluctuations or simple cycles in the mix of electron, muon, and tau neutrinos arriving, UCTE predicts a non-random flavor oscillation bias, a systematic drift in the flavor ratios that isn't cyclic and, crucially, might correlate with the large-scale structures the neutrinos pass through.
So the journey itself imprints on the flavor mix.
That's the idea. They carry a memory of the coherence fields they traversed. Big underground detectors like Super K, IceQ, DUNY, and the upcoming Hyper K are the kinds of experiments that could potentially look for this over many years.
Fascinating. And one more, plasma coupling.
Plasma neutrino coherence coupling. This is about looking for correlations between maps of cosmic plasma, like those made from synchrotron radio emissions, and the predicted locations of these neutrino phase density zones or condensates.
What would the sign be?
You'd look for subtle weirdness in the plasma. Low-level plasma oscillation irregularities, maybe zones where synchrotron radiation seems oddly suppressed, or irregular Faraday rotation measures, things that suggest the plasma's behavior is being subtly disturbed by an underlying coherence field. Radio arrays like Planck, LOFAR, and the SKA would be vital here.
So all these tests together, they're trying to map this hidden layer of reality.
Essentially, yes. To map the invisible architecture of coherence fields embedded in galactic systems and see if it matches the UCTE predictions.
What an incredible journey we've taken. We started with the neutrino as this familiar yet still mysterious ghost particle from the standard model. And now, through the lens of UCTE, we've explored this radically different view. The neutrino as a coherence residue, a phase-drifting node, maybe even a fundamental cosmic architect.
We've seen how UCTE rethinks everything from why they're elusive to where their mass comes from, not Higgs, but this coherence damping and how their flavor changes are seen as rotations in this abstract phase space.
Plus, this whole new idea of neutrino condensates potentially shaping galaxies.
Yeah.
It's a lot to take in.
It really is. And that leads us to the final thought we want to leave you with today. Consider this. Maybe the neutrino's defining traits, its near invisibility, its minimal interaction, its shape-shifting identity, maybe these aren't just weird quirks or anomalies. Maybe, as UCTE suggests, they are actually signatures of its deeper ontological role.
Signatures, meaning clues to its real purpose.
Perhaps. Suggesting the neutrino isn't just some dead remnant of particle decays, but an active resonance, alive in the universal breath of coherence. Maybe its invisibility isn't a weakness, but reflects its higher fidelity to the original symmetry of the universe. It could be the whisper of the coherence vacuum, still present in our dimensional world. So the question for you is, what stands out most to you about this radical reimagining of one of the universe's most enigmatic particles?